All right, so here we are for the second part of chemical equilibrium, where we are going to talk about some ice tables. So the first thing we're going to do here is we're going to start out with a fairly simple calculation of our equilibrium constant for the reaction below, given the concentrations listed in the question. So we're going to write our equilibrium equation or expression, and as I said in the last video, right, we don't have solids in there, so our tin oxide and our tin are not going to show up in our equilibrium expression. And to calculate this, all we do is we fill in the values from the problem into our equilibrium expression, and we do a little math, and we come up with a number, 6.34 times 10 to the 7th. Great, easy enough. Now we're going to move on to something that's going to involve some more steps. And so we're going to want an ice table, right? Because in this problem, we are not given equilibrium concentrations of everything in this equation, so we can't immediately calculate the value of our equilibrium constant. So what we're going to do, we're going to set up an ice table that's going to look something like this. And it is called an ice table because we set it up as our initial concentrations, the change in concentration, and the equilibrium concentrations. And so we're going to fill in all of our information here from the problem, given that we have initial concentrations for hydrogen and iodine, which we have moved into our ice table, and an initial concentration of 0 for our products, right? Because at the very beginning of our reaction, we tend to have no products, though that might not be always true. And then we have an equilibrium concentration for our product, right? Hydrogen iodide. So we're going to fill in all of those. We can then fill in the change for our product, right? Because we know if we started with 0 and ended with 1.87 times 10 to the negative 3, that we had a change of positive 1.87 times 10 to the negative 3 molar. Right, and if we look at our reaction stoichiometry, which is 1 to 2 for both of our reactants to our product, we know that the change would be negative half of the change for our product, right? Because if we have a change of concentration that is 1.87 times 10 to the negative 3, right, and our stoichiometry is 1 to 2, right, we have half the amount of change for our reactants, right? So both of them are changing in the negative direction, right? We're using up reactants here while we're making products. We just do a little subtraction and we find our equilibrium concentrations for our reactants. So we now have equilibrium concentrations for everything in our reaction, which means it is time to write our equilibrium expression, right? Products over reactants, and put some numbers in, right? Which again, now we're just going to do some math, and we end up with 51. Okay, so at this point, I think you're probably asking, okay, what if we don't know the equilibrium concentration? What do we do then? Well, what we do then is we still are going to write an ice table, which we have here. We're still going to fill in our initial concentrations, right? Because chances are we know how much of our reactants we put into our flask. And then we're going to reach into our mathematical bag of tricks and pull out some algebraic type looking things, right? We are going to define the change as positive 2x in our products, and the change is negative x for our reactants, right? Because we are losing some amount of our reactants, and because our stoichiometry is 1 to 2, we are gaining twice as much of our product as we lose for each of our reactants. And then we set up our expressions, right? Where our equilibrium concentration of our products is the initial concentration minus the change, which in this case is x. And then for our equilibrium concentration of our product, right, it's 2x. So we have our equilibrium concentrations for our reactants and our products, which we now can write our equilibrium expression, right? Same as before. And now we put in our expressions from our ICE table, right? We were told what the equilibrium constant is for this reaction, and we have our expressions for our equilibrium concentrations for everything. Now, to solve this, right, we're going to want to rearrange what this looks like to this, right? So we have just moved our 50.5 over and simplified our fraction expression there with all of those bracket or parentheses and numbers minus x and all of that. And for those of you who remember your algebra, and hopefully that's all of you, you will know what's coming next based on the format that we have simplified this into. And if you said the quadratic equation, you would be very correct. So we go ahead and set this up in our quadratic format so that we can actually solve this and get a meaningful number out of it. And as those of you who are familiar with the quadratic equation know, we get two values out of the quadratic equation. In this case, only one of them makes sense, right? Because we get 2.3 more or less and 4.8. Now, 4.8 in this case makes no sense, right? We cannot have a negative change of 4.8 molar if we start with 2.5 and 4 molar, right? That will give us negative molarity for our equilibrium concentration. And that's not something that you can have, right? You can't have negative molarity. So the change is going to be 2.266 for our reactants, and a change of 4.532, or double the change of our reactants for our product. All right, so we now have actual equilibrium concentrations for all of our species. Okay, so now you're saying, that's great and all, but what happens if we're not even at equilibrium? So we have something for that, which is Q, right? This is our reaction quotient, and it is used in place of our equilibrium constant in an expression where the concentrations or partial pressures are at any point during the reaction not necessarily at equilibrium, right? So for this generalized reaction, we write an equilibrium expression, but instead of putting Kc or Kp, we simply put Q to state that the reaction may be at equilibrium, but also may not, right? And we can tell whether the reaction is at equilibrium by comparing Q to our equilibrium constant, right? Because if our value of Q is less than the equilibrium constant for that reaction at that temperature, that means that equilibrium has not yet been reached and will continue in the forward direction or forming products. If Q is equal to K, simple, reaction is at equilibrium. And if Q is greater than K, the reaction has passed equilibrium at this temperature and will go in the reverse direction, right? Forming reactants. Okay, so now that we know about Q and all of that, we can talk about the Chatelier's principle, which states that if a system at equilibrium is disturbed by a change in temperature, pressure, or a component concentration, the system will shift its equilibrium position so as to counteract the effect of the disturbance. What that means is, if you change something about a system at equilibrium, the system will work to go back to equilibrium. Okay, so how does this work with changes in concentration? When the concentration of any substance, when the concentration of any substance in a system at equilibrium is increased, the system will consume some of that substance to reestablish equilibrium. When a concentration of a substance in a system at equilibrium is decreased, the system will produce some of that substance or consume the others to reestablish equilibrium. It might look something like this, where if we have this reaction where we have 2 plus 3, right, at equilibrium with our 2 red dots there, and we add some blue reactant, right, what's going to happen is we're going to use up some blue and some orange and make more red to reestablish equilibrium, right? Because when we added more blue, we're forcing things over to the product's side. Now, changing pressure. When pressure increases, the equilibrium will favor the side of the equation with the least moles of gas. When pressure decreases, the equilibrium will favor the side of the equation with the most moles of gas. All right, so decreased pressure, least moles of gas, increasing the pressure, right, squeezing the gas, equilibrium will favor the side with the least moles. When you decrease the pressure, right, more space, equilibrium favors the side with the most moles of gas. So if we have this situation where A is in equilibrium with 2B, all right, something like this, where the blue dots are A and the red diamonds are B, right? If we increase the pressure, right, the reaction tends to move back towards the reactants, or A, right? We form more A, because that is the side with the least moles of gas. Whereas if we decrease the pressure, right, the equilibrium is going to move further towards products, or more B, right? We use up more A and make more B, because it has more moles of gas. It has more area to fill up. Okay, here's the one that I think tends to make the least intuitive sense for people, but really is no different than the one where you're changing products and reactants, right? So changes in temperature. The big difference with changes in temperature is that unlike pressure and concentration, the equilibrium constant K is almost always changed, right? We can, however, still make generalized statements about which way it will shift based on if the reaction is exo or endothermic, right? So in this case, right, we treat heat as either a product or a reactant, right? We treat it as something that is added to the reaction or produced by the reaction, right? So exothermic, we treat it as a product, right? Whereas endothermic, we treat it as a reactant. And so now, just like changing the concentrations, when we add heat to something, right, it's like we are adding either a product or a reactant, right? And it's going to shift the equilibrium to the other side, right? So like if we add heat to an exothermic reaction, right, it's going to push the equilibrium back towards reactants. Whereas if we add heat to an endothermic reaction, right, it's like adding a reactant. And so it's pushing the equilibrium towards products, right? So what we can say is with exothermic, increasing the temp increases K, endothermic, increasing the temp decreases K. Okay, and that's it. We'll talk about this more in class and we'll do some practice. I'll see you soon.